Good morning, good afternoon, wherever you may be in your day. Thank you as always for choosing to make chemistry part of your day. We're going to talk about solubility rules here, and I'm going to have to start with two caveats here. I use a simplified version of the solubility rules, and I will say most instructors, whether at RU or other universities or high schools, have different ways of treating this. Some people will give you the rules and ask you to apply them. Some people have you memorize them with the exceptions. Depending on the textbook you use, the list of soluble and insoluble ions changes slightly. And this is not to mess with students. This is not because we get together and try to think of ways to make students' lives harder than they already are. This is due to the idea of things are soluble or insoluble. Everything is soluble with everything. It's just the extent to which it's soluble. Is it one molecule per whole ocean? For that amount, you might say, really, that's irrelevant, and we could certainly say that's completely insoluble. And likewise, you're going to hit a maximum amount of solubility for a compound, even though sugar goes into water at incredible amounts. If not, make some Kool-Aid, you'll see what I mean, or sweet tea. There is a limit to how much sugar you can put in water. That's how you make those beautiful rock candies, if you will. Is going past the solubility limit by heating and then cooling down gradually and letting it sit over time. So I do want to say there's a lot of gray area with this. So everything I'm about to do, I'm going to treat as if it's a black or white issue, a yes or a no. And with the understanding that I understand that's not true. And there's some simplifications here and exceptions that I'm ignoring that I'm aware of and all of these other things. So with that caveat aside, let's start. All right, so typically when we talk about solubility rules, we're talking about ionic compounds in water. So just to be clear there. So we're talking about ionic compounds, so that's typically things that start with a metal and have a nonmetal. And we're in water is the implication here, even though this would be very different if we changed our liquid, for example. If we use gasoline, very different. If we use alcohol, very different. So we're talking about water, we're talking about ionic compounds, we're talking about solubility. So these things are typically solids. We throw them in water, we have two options. They will dissolve. The cation will get coated in water. The anion will be coated in water. It'll act as a strong electrolyte, and those electrolytes will act independently in solution. Or it'll be insoluble. They'll attach to each other much stronger than they do the coating of water, and they'll stay together and they'll just sink to the bottom of the beaker, cup, whatever you have, bucket, whatever you have. And we would call that insoluble. Okay, so chemistry is a happy, positive place. We always start with the cation, we start with the metal, we read left to right in our culture, so same thing on the periodic table. So let's start with the cations, the positive charges. These are much simpler. All of your group 1 cations and all of your polyatomic cations form soluble salts. So we would call these AQ, we would break them apart, we'd represent them that way. So just as a reminder, group 1 is the first column of the periodic table, so hydrogen, lithium, sodium, potassium, rubidium, cesium, those would form soluble salts. Likewise, the only polyatomic cation we have you memorize is NH4. So these 7 things would form soluble salts. So if a molecule starts with these 7, we're going to assume soluble, AQ, break it apart. Everything else, we're going to have to look at the anion. Now, if you have this, you don't even have to look at the anion. Regardless of anion, these are soluble, you move forward. If we don't have one of these 7, so if we started with copper, cobalt, iron, something like calcium, we got to look at what it's attached to. So, the good news is you've already memorized this, you just haven't realized it. So, we memorize our 6 strong acids. There they are, in order, once again. And if we take the H part off, so again, if we break these apart into what a strong acid would really be, and we ignore the H's, or in many ways, if you just want to take your eraser and just look at the back end of your strong acids, look at those special effects. If we take away that, what's left behind, that's what we're looking for. If those things are there, it's going to be soluble. If they're not, then it's going to be insoluble, and that's our default. So soluble, it's going to be AQ. Insoluble are going to be solid. And of course, because nothing's ever quite that simple, we got to add one to our list. And again, every book's a little bit different. Every teacher may or may not go along with the book as written. I'm going to add one to our list. So we have the 6 ends of a strong acid, chloride, bromide, iodide, nitrate, sulfate, perchlorate. I'm also going to add in acetate, C2H3O2-. So I'm going to add in acetate as well. The rest we're going to assume are insoluble. I am personally, for my class, going to ignore the exceptions. Most teachers will not do this, so just be aware. There is one exception I expect you to know because we use it all the time in lab. Is this chloride check or chloride precipitation reaction, which is silver. If you use silver ions, silver and chloride together form a solid. Normally our solubility rules would say chloride's soluble. It is not. So silver chloride is the one exception I want you to know because we use that a lot. We'll also use in lab as an exception barium sulfate as a precipitation reaction, so I want you to be aware of those two exceptions. There are more. Most of these ions have 2 or 3 exceptions associated with them. And if you're generally speaking wondering about the solubility of ions, if it's a +1 with a -1, it's almost always soluble. If it's a +2 with a -2, it's almost always insoluble. So if it's and 3s would be worse. So if you got 2s and 3s, the charge is so large they just stay stuck to each other, they don't attract the water as well, and they stay stuck together. We actually call this lattice energy if you're curious about such a thing. But anything with 2s and 3s, insoluble. 1s and 1s are going to be soluble. Of course, there are a couple exceptions to that. And if it's a 1 with a 2, that's kind of gray area. Depends on what it is, and then we got to apply our rules. Okay. If we want to summarize this, if it starts with this or ends with this, it's soluble. We're going to call it AQ, and we're also going to break it up. Anything else on the front end? Anything else on the back end? It's a solid. We just leave it alone. We're done. It's a precipitate, typically. And one common mistake people make with this is they say if it ends with Cl. So if we look at MgCl2, you might think that's different. It ends with a Cl2. That's not Cl. And I know Dr. Werger says these things matter. These little differences matter. There's a difference between Cl and Cl minus. Difference between chlorine and chloride, or nitrite versus nitrate versus nitride versus nitrogen. And those things really matter. And that's true. And good for you for picking up on that. But what we really want to think about is what's this composed of. It's not composed of Mg and Cl2 chunks. There's only one capital letter in front of the 2. Remember my whole cutting the head off thing? So we bring that 2 out front. It's really Mg and 2 Cls. So that indeed is made out of chloride, and this should be soluble. You can have the same thing on the front end. You could have something like Na2CO3, sodium carbonate. And this also, again, when we cut that head off, we look, there's only one capital letter in front of that 2, so that means it should come around front. We really have 2 sodiums and then a carbonate. So that sodium is on our list, and that should be soluble. That might cause less confusion because it literally looks like an Na starting with an Na. Quick practice, soluble or insoluble, solid or aqueous, and here's some random salts. Ammonium carbonate, sometimes this throws people because it doesn't start with a metal, but this one's great because they got it in parentheses. That should be a little ding, ding, ding light on top of your head telling you, oh yeah, this is an ion, and there's my break. So NH4, ooh, polyatomic cation, soluble. I know this one, AQ, done. If I go to the next one, FeBr3, I find iron. It's in the middle of the transition metals. Oh no, that's that area where we don't, it's usually complicated and a big question mark over it. So that's not going to help us. So once again, we got a question mark here. We go to Br3, and I got to really think about this. Is it a Br3 polyatomic, or is it 3 Brs? Good, it's 3 Brs. So that's Br minus. That is on my list. That's going to be soluble. That's an AQ as well. Calcium oxalate. Once again, you might not have memorized oxalate. You might not know what oxalate is. But I do recognize a metal up front, and I cut that off. I look at calcium. It's not in the first family, so that's a question mark. I look at this thing, and I'm like, I don't know what that is. But it's not on my list. Definitely not part of a strong acid. Definitely not acetate, so that's out. So again, if we have 2 question marks, we put a solid. And calcium oxalates actually can cause kidney stones or gallstones in your body, which are clearly insoluble and unfortunate at that regard. Aluminum chloride. So again, I see a metal. Let's cut that metal off. Aluminum, not on my list. It's not in the first column. Chloride, again, this is much like Br. It's really 3 Cl minuses, so that's a yes. HCl is a strong acid. Do the same thing here. Potassium's a metal. Cut it off. Potassium's in the very first column. That's a yes. I don't even have to look at the back end. Titanium sulfide, that's a metal. Cut it off. Titanium, oh no, it's in the transition metals. Ah, run away, go to the anion. We do that, we come over here to sulfur. And again, This really should be viewed as 2 sulfur ions and not an S2 block. But regardless, not a strong acid if we put a H out front, and not on my list, or however you want to look at it. So this is going to be by default another question mark. So this is going to be a solid. Hopefully that's helpful. That is kind of the basic premise of these solubility rules, and if you're really doing research or something in the lab, there's going to be degrees of solubility, and you should either look these things up or determine them yourself using some type of equipment. Thank you so much. Have a wonderful day.